Recording. Let's go to Brightspace. Take a look. So you guys are section 1. Okay. So we are going to get started today. So we finished cross entropy last week. We covered this topic. So we've started our discussion of loss functions. We will continue to go over that in the next these slides here, performance metrics, and also loss batch norm. So these are kind of like theoretical. This is going to be some examples with PyTorch. And then obviously we're currently on week 11. So I remind you that week 12 is exam number 2. So a week from today is your exam. Okay, don't miss the exam, please. So it'll be here. And that's kind of the end of the second third of the semester. So we're like 66% done, somewhere around that. Today we're going to focus on the project, right? So that has been assigned already, and you know about it. I discussed it last week, and I gave you a brief introduction to the term project. So you should form your groups. Remember, I think I said no less than 2, no more than 3. So make sure you start doing that. You have about 5 to 6 weeks because you have to present the last week. So really, I think you have like 5 weeks for this project. So you're already behind. All right. Yeah. So that's the idea. So today I'm gonna go over the topic. Discuss it formally. Okay. So that's gonna be this one, neural input optimization. As I said, I've already kind of indicated what the goal is, but all of you need to have your own data sets and your own problem that you're solving. Okay. Today I'll give some ideas. This is by no means the only approaches, right? So don't just go with what I'm listing here. Create whatever it is that you can do for the project. Okay. So here, so let's get started. And we are recording. I do have some scripting examples, some PyTorch examples, but it's pretty straightforward. But I do have some examples. All right, so everything will be on this repo here, neural input optimization. So you can click on it. And so this is kind of the repo that I've been putting together, the README with code examples. And so we'll discuss this today. And I do have some examples here, and there are other examples as time permits, right? So I mainly have just this week to cover this topic. So make sure if you don't understand that task question. But I will be introducing a lot of things today, including, if you remember, I said that you learn how to do an MLP and a deep learning, right, and all that. But I actually mentioned that I don't usually go with those, and I just have this thing called a residual net. And so that's what I'm going to be using for this example, actually. So you can also use it and play with it. So add that to your arsenal of, keep in mind, a lot of the things that we'll be doing seem like regression, but regression, as we saw, can be converted into classification easily by just some kind of a sigmoid function, softmax function. Okay? But essentially, you have multiple inputs that are regression values. This is very common. And now you'll have multiple outputs as regression, right? All right, so the places, remind me not to forget about this topic, deployment. So this is one thing additional that I will add to your term project, and that is that you need to deploy the model. You know how you're in your current homework, you're deploying via Onyx, right? And we've discussed that, but NIO does not easily deploy via Onyx. And you need to understand why, right? So that's one of the things that we're going to discuss. I have a suggestion for something called Fast API. So don't know if you've ever tried it, but that's a potential solution. Got it? All right. So we'll talk about the topic, but mainly a lot of these things are so that this is what I want you to do for your term project. And so you need to start looking at some data sets, etc. A lot of the examples live here, and there's a little bit here in deployment. I may have some data sets under data. Yeah, I do have, right. So I have some veterinary medicine data and a few data sets in there here and there as I've been playing with this idea for different applications. Okay. So let's get into the text of it. All right. So let's talk about this. Whoops. All right, so neural input optimization, NIO, is a technique that uses a differentiable surrogate model to reverse engineer optimal input values given desired outputs and constraints. Okay, guys over there in the back, any questions? Okay. All right, so optimal input values given desired outputs and constraints. So that's the idea. Rather than relying on black box search or trial and error methods, NIO trains a forward model, typically a neural network, although a neural network is actually not needed. You just need some kind of a set of functions that are differentiable. Differentiable just means that stochastic gradient descent can be applied. So that's essentially what that means. So NIO trains a forward model, typically a neural network, to learn the mapping from input variables to output variables. Once trained, this model is used in reverse. It enables gradient-based optimization of inputs by minimizing a constraint-aware loss function, effectively inverting the system to find suitable inputs that yield the specified outputs. Okay. NIO has broad applicability across domains such as engineering, finance, healthcare, and material science, where stakeholders often know what they want as outputs, e.g., like performance goals, target prices, biological responses, but must determine feasible inputs under real-world constraints. I can't stress how important this is in a business setting, right? So, yeah, a model is great, but it's no mystery that's being solved. Do you see what I'm saying? Essentially, you already knew that, right? And you're kind of just optimizing it, given inputs, given outputs. But in any business setting, there's always this like, wouldn't it be nice if I could figure out what these things need to be for me to get this outcome? That's a different kind of a problem, okay, than just your regular classifier or regression model. Another important point is, yes, you could try out randomly or by trial and error a lot of inputs to see what outputs you get. But so this statement here, rather than relying on black box search or trial and error methods, NIO trains a forward model to learn the mapping from input variables to output variables. Once trained, this model is used in reverse, and it enables gradient-based optimization of inputs by minimizing constraint-aware loss functions. This is the tricky part for you guys in the project I've mentioned. Today, I'll probably do like 2 examples already of these because these are going to vary based on the problem that you have. So effectively, and I've mentioned this, okay? So in material science, for instance, I gave this example. What if you want to create an alloy, right, or a composite material that has these properties like level of brittleness, stiffness, the melting point, right? What's the temperature? So you can basically, collect some data about that and then figure out what inputs of your process, of your furnace, whatever it is, would produce that type of material. Do you see that? Same thing in molecules, things like that. So it's really, a useful thing. Okay. And that's where it has been used mostly, right? So in the areas of physics, material science, chemistry, right? AlphaFold, I think, kind of is like this. In AlphaFold, you design a a composite molecule given some inputs that you want. So in essence, maybe here you're reversing it a little bit. If I have this, what would produce it, right? So, but that's the idea. It can be considered a generative model also, right? Because you can generate more than one if you'd like cases. And I gave the example of secure password generation, for instance, right? So that's something that you can do. For example, a veterinary use case might involve identifying safe and effective dosage combinations of antibiotics based on desired recovery outcomes and species-specific tolerances. So that's an important thing, right? So you're like, well, this is a dog, not a cat, or this is a bird, or this is, I don't know, fish, right? And so based on these characteristics of the output, you consider what would be the combination. And that's the great thing about this also is that it's multiple variables, right? So it would be a multi-input vector, and it's going to try to find a balance, not just for one variable, but for all variables via stochastic gradient descent. Do you guys see that? So that's the use case for it. In this way, NIO acts as a decision support layer that enables fast controlled experimentation across complex multivariable systems. Okay. So let's take a look here. So some of the examples I have is this one in cybersecurity. There's a pretty complete, this is a paper, so it's a pretty complete piece of code on generating secure passwords, right? So that's for you to look at as reference. We'll probably not cover this one today, as we'd have to go into some depth, but that's like a third example that I could cover potentially next week. Okay. Another example is industrial blast furnace applications. I've described this a little bit as well. We'll cover this one today. Just go over some of the ideas of the code so we can talk about it. Reasoning. So reasoning is, this is a type of reasoning, right? How many times do you have a problem? You're driving to the airport or whatever. I want to get there at this specific time. I want to avoid traffic. I want this or that. I also need to pick up some food on the way, right? So multiple variables. And I want this food, not that food at this price point. And I want to spend this much gas because it's a work-related thing or something like that. So what do I need to do, right? So what are the things? What road do I take? What toll road? What, all these things. So that is my point is we do this all the time, right? Aren't we reasoning about this, right? And at the end of the day, we maybe just as humans, likely we can only hold like 3 variables at the same time in our head, right? And find the optimal outcome for just those 3 variables. Machine learning does not care about 3 variables, right? And this method, because it's constraint optimization, just like we train, how are we able to train all the weights for an image that has 784 pixels? Do you see that? And machine learning can, so why not, go beyond these 3 variables that a human can reason about and do way more. So that's the nice thing about it. So you can think of this idea of neural input optimization as also reasoning, right? But it requires, and this is one thing I want you to understand about this, which is now this is touching on it also the fact that we can deploy it on Onyx is touching on this problem. It's not a problem of it works, but it's a problem of implementation currently. So what does NIO require? It requires AutoGrad. AutoGrad right there. What is AutoGrad? We will see this in a week or two. And it's essentially the engine in PyTorch that calculates the derivatives. And we've talked about that briefly, how that is the way that we know if we're going to add or subtract, the values, the learning rate from the weights, right? So that we can do the update. This is a process that is facilitated by PyTorch. PyTorch uses that mechanism to train neural networks, a model, and then those models are exported and deployed via ONNX. But the engine of AutoGrad cannot be deployed. Do you see the problem? So pay attention to this, because you will have to deploy your model, right? Which means you have to build it in such a way that you have AutoGrad deployed, right? So the way to do it, you can't do that with ONNX. ONNX doesn't, as far as I know, does not have that capability yet. But you essentially have to deploy it almost like a service call. Do you know what I mean? Like SaaS or one of those things. So you have to have either, an actual environment running Torch, right? Either on Docker. Docker containers are a famous approach, but you can just do it on a Linux machine, and then have some kind of an API, like Fast API, which is a library that allows you to essentially implement sort of your own API. And everybody, I think, knows what an API is, right? So essentially, that is the approach that you would have to take. Why? Again, because of the differentiation. To be able to update the weights, if we just randomly update the weights, and there's no point, right? It would be like if you had to train ChatGPT or just regular models randomly. That's crazy, right? We do it via AutoGrad because we can differentiate and know when to add and when to subtract. So essentially using stochastic gradient descent, right? And that is the key to this mechanism, but it's currently also why we can't deploy via ONNX. So we have to use something else like, a Fast API and just run it as a service on a machine. Make sense? Any questions about that? All right, so that's an important point. So going back to this idea of reasoning, if you think about it, right, we reason about, what are these three variables that allow me to get there on time and maximize my fuel consumption and all this, and toll roads and things like that. So we reason. How do we do it? How do you do that? But I want you to really think about this, right? As you start to understand NIO more and more, think about this. How do you do this in your head, right? Is it a neural network? Are you taking derivatives of functions in your head? We don't know, right? But at least we do know that stochastic gradient descent, because we're seeing it here, can do it. So we may not, as humans, use stochastic gradient descent, right? So we don't have possibly that, but AI can use it in this way. And now the question that I might ask you guys is, could we implement NIO into the transformer, the GPT? So you guys know that a GPT, you guys have seen the GPT architecture. You should understand it by now, how it works, right? We just add layers. You will learn how the code here works with NIO. It's just more code, more neural networks and things like that. Could you insert a new set of blocks, NIO, and then give something like the GPT the capability not just to produce text, but in some kind of a recursive loop, start to reason through, okay, what are the 7 variables that I need in this input to obtain these 11 variables in this output? Do you see what I'm saying? It seems like it's possible, except for one problem. Again, what is it? The differentiation, AutoGrad. AutoGrad exists outside in PyTorch. We use it to update the weights of the model, including the weights of the GPT. But how would we update the weights of the input inside the neural network itself? Do you see that? We would have to have an AutoGrad in there. How? The only way that I can think of that we could do that is we would have to train a set of neural networks to be neural network autograds somehow. But I mean, some of you have taken calculus. Didn't you learn how to differentiate? Yes, you did. Right? And so a neural network could also do that potentially. Do you see that? And then if you can differentiate like AutoGrad does, then you could probably reason even further. So in any case, whether this works right now or not, think about it. These are ways that we can enhance the intelligence of GPTs to be even better. Maybe right now they're getting like 80% of the way, but they're not using stochastic gradient descent to arrive at the optimal answer. So eventually this gives it that last 20%. Do you see that? So anyway, those are research problems. I'm sure that actually this paper here, I included it. You can read it if you're interested in it. It's already trying to do something like that. Okay, so you can see people are already trying to make these GPT models even smarter. All right, and this is an approach. I think the name is reasoning through optimization, embedding a learnable calculus engine in large language model. So yeah, but anyway, my point with those two examples is for you to understand the differentiation, the autograd that happens in PyTorch, not in the neural network. And this is a limit currently for reasoning, for deployment. So for reasoning, you don't have a requirement like that for your assignment, but for deployment, you will have that requirement. So you will have to figure it out. My suggestion, fast API probably, so that you can run, and probably it'll be like you run it on a machine and then you make the call, like a client server architecture type of a thing. Does that make sense, guys? Any questions on that idea? No questions? All right, great. All right, so I'm trying to give you as many ideas as possible, right? And then we'll just dive into the code, which I think you will find is actually pretty easy. The simplest example I can give you, I have like a baby NIO example, and then the other ones can get more complex. But certainly, I have said many times, and I think this is true. If you do good work on some interesting problem, you could even possibly publish this. I mean, it's just up to you don't have to have massive amounts of data for this one either. 5,000 samples might be good enough. All right, so let's move on a little bit. So that idea, reasoning, I wanted to discuss it a little. We do have a paper on token generation. You can see I don't have the link yet because the paper is sort of not public yet, but as soon as it is public, I will add that here. The code, though, is already here. So you can take a look at that one, and I might next week maybe discuss it a little bit more. So these are ideas that you can consider. So in this example, we consider neural input optimization, a method for inverting an AI model by optimizing its inputs to achieve a target output. The goal is to simulate here an audit scenario, such as what inputs would cause the model to output a risky, sensitive, or policy-relevant value, even while respecting constraints. So this simulates how an attacker or an auditor, good guy or bad guy, right, might find borderline inputs that pass policy checks but produce dangerous or unexpected outcomes. So here, the examples are down here, but I need to rearrange this. So I'll come back to this idea. I have some examples of LLMs and how you might consider that. So the scenario is we define a simple pre-trained model, FX, right? This is just a model, a neural network, and then use gradient descent to search for an input xopt such that xopt provides the desired output. That's it. That's it. And we don't even need to have data when we're doing this optimization because you can define losses. And I'll show you examples of that today, at least two examples, but there may be more, right? So, and that's one of the really nice aspects of if you guys do this as a real research project, you come up with some clever idea, something interesting for a loss function, for your problem, and that, could be very interesting. So X op stays with, and also we can constrain the range of values of the Y target, or also constrain the values of the input, right? So for instance, there are things that are non-physical, right? So temperature, let's say negative temperature, right? So then you would limit it to 0 to something else, or producing, I don't know, some amount of Kelvin somewhere on a device, right? So that's not going to happen. That only happens in the sun. So then you don't need to go beyond those ranges, and so we can constrain things. That's why this has a lot of properties related to like physics, chemistry. So that's going to affect whatever you're doing. But at the same time, as I said, we applied this to password generation, right? So that, yeah. We can put limits. The goal is to find the answer. So that we put let's say that I want specific amount of temperature and specific amount of pressure to go into something, right? That's right, to get the results. But also, there's limits to the amount of temperature that we can put in. So we explicitly provide that to the model because, in physics, right, that would never happen, but a model can extrapolate to anything. So a model could start thinking, okay, 80 bajillion Kelvin, right? Why not? It's a number. So we do this just to constrain it so it's more efficient and but if we are asking for what that that's what's supposed to do, like making some links between what we are asking and what we're supposed to do. Yeah, we have a model. So let me switch to the whiteboard, maybe. Might be a whiteboard moment here. Okay, great. All right, so NIO has two passes in its most basic case. So step one, step two. Step one, we just train a model exactly like you've learned. There's like nothing different. Here I'm going to assume it's a multi-input, multi-output model. Let's say this one has 7 inputs, this one has 3. For whatever reason, we train the model, train the weights, everything's good. This sometimes is called a forward model because it goes in that direction. These are the inputs, these are considered the outputs. Consider that, and I do have an example, right? So we'll get to it. But just to address your question, so let's say, let me actually look at some real values because it'll be easier then. So the outputs are really what matters here. So the outputs would be gas temperature. So it's going to be 3 neurons. So one is gas temp. The other one is hot metal temp. And the other one is the temperature of the nozzles that shoot like natural gas or something like that. Those can get very hot or very cool. So let's call it a raceway. So I'm going to call it raceway flame temp. Flame. temp. Let me move this also. Okay, so this is, you guys know, we live in this area. It's very well known for steel mills. Here in Gary, we've got US Steel, all that. They produce steel. All right, so the variables that go in here would be things like something that makes sense, H2 temperature, right? So that's a win rate, natural gas rate. So that's the amount of natural gas that you're injecting. Sometimes you can, I believe if they put in a lot, actually it cools it down. It's weird. And then if you have very little, it's hotter somehow. So do you see what I'm saying? So it's like the knobs of the furnace, and then it produces variables, and those variables determine the kind of steel that you're going to have. And that's really great because then you know if that steel is worth, I don't know, $100 a ton versus $200 a ton. So that's important, right? It doubles your profit. So it's really critical. So then you've trained the model. Now what you want to do is you want to frame the question like this. I want to find out. So in step 2, now we go in step 2, you freeze the weights of this model. So these are frozen, okay? So you freeze the weights. I'll show you guys how to do that. It's super easy. So you freeze the weights, but you start with an input. We're going to call it Z. That is random. And sometimes it can be random with some distribution. So that's also a thing. But for simplicity, let's consider it to be random. We make this one to require gradients, which means that, you know how when we use stochastic gradient descent to update the weights of the model? Well, the term for that is that all of those weights require gradients. They're differentiable. So that means that when you do the loss optimization, those weights get automatically updated in the computational graph by PyTorch. Okay, so what we do is we flip the switch. The inputs were never, as far as you know, at least in this class, we never made them that they would require gradients or be differentiable. Do you see that? Now we flip it. And now here, we grab this same model. I'm going to use a different color, actually. What looks frozen, like a light blue? So light blue because it's frozen, right? So the weights are not active anymore. So here, this was blue because it was frozen. Now this one is red because it's not frozen. Do you see that? And that's it. And then we have the outputs here, same 3 outputs, but now we say, find out what this input is that gives me the following outputs. And now let's quantify it. I want, and I'll write it down. So there's still the 3 variables. So my requirements are, I want top gas metal, which is the same as gas temp. Gas temp. I want the first one, top gas temp, to be greater than 100 degrees Celsius. Do you see that? So I start to constrain it. These are the constraints that you have to implement in the loss function. I want my hot metal temp to be greater than 1700. And that's some unit. Oh, Kelvin, I think, K. And then I want my raceway, yeah, temp to be between 1700 and 2000 and what is it? 2000 or 2100. Do you guys understand? So this is what we do. We want these outputs because we know that if we have material like this, steel or whatever, we're going to get $50 more per ton. But so what's going to happen is in a loop or iteratively, we are going to run this one, the bottom one, the second one. We start with a random input, run it, produce something, compare it to the constraints, minimize the loss, backpropagate. What do we backpropagate? Well, we backpropagate in the whole network, but what do we update? The only thing that is differentiable, which is the input itself. Do you see that? That doesn't mean that in one iteration we get the solution. So we have to do it multiple times. So then this input goes back in again, produces another value, hopefully a little bit closer to what we're looking for. And we just do this, I don't know, 20,000 epochs or some number, right? And what should happen eventually is that this input starts to become pretty close to what it should be. It may not be perfect. I mean, that's because at the end of the day, your data that you use to train this model may not have all the information necessary, right? But essentially, you think of like, if in the case of furnaces, it's like you're learning the physics of the furnace. And then now the furnace is acting like an oracle of knowing the physics of things. And it figures out what input would produce a given output. And this is one application. But like I said, you can also generate passwords with this. And I've suggested this idea that maybe you can even generate images. Because what is an image? An image is just, if we take an image that is what? Yeah, but I'm trying to think, 24 by 24, right? If we make that into a vector, is 784, I think. I forget. Yeah, 28, I think. 28 by 28 is 784. And then this just means that this vector is 784. This could be whatever it is, right? 784. Images going in, images coming out. And once you get the vector, you despaghettify it. So just make it back into a 2 by 2 and generate the image that was produced. Do you guys see that? So applications, that's why part of the project is it is your term project. And part of it is I'm leaving it open-ended for you to pick a topic. So you can go as easy as this one, chemical things. You can do passwords or something related to that, or be more creative, right? So it's up to you. And like I said, I will provide some examples. But yeah, did I answer your question?
But life, like, okay, now I have my knowledge.
This one, the one I just gave you. Yes. So think about it. You're operating you work in a chemical company. So you're a chemical operator. You have all these knobs, and you know that you want steel that meets this condition because you want to make that extra million that year, right? So then how do you do it? Well, you're not just going to randomly turn the knobs. What usually happens is you have like one person at the company that's been there for 30 years. So they're kind of like, I know if I do this and this, that's the best. But that may not be the optimal. And they're leaving money on the table. Do you agree that by stochastic gradient descent, it's going to say, well, actually do this a little bit and this a little bit. And now it's going to be just that a little bit more percentage. Yeah.
So the first step is have like X, Y, then you go to Y, and the step 2 is like, okay, we have the Y that we do, and when we want to find X.
We don't have any data. You could have data. Say it again. Sorry, I interrupted. We have.
We have the results that we want, but then we're gonna find a way to find the X.
So step one, we just train. So you have both X and Y. Like any model, like iris or wine quality data, we had inputs and outputs. We just train the model so that when we give it an input from the data set, we're going to get the corresponding. Yeah. Yeah. But that doesn't mean that we can all we can do is give it inputs that already exist in the data. But what about a case, an output case that doesn't actually exist in the data? Do you see why it's generative now? Because I may not have a case that is greater than 100 and greater than 1700 and where this one is between 17 and 2100. I may not have that in my data. But wouldn't it be nice if I could figure out what that is? Yeah.
Just because of the model train, they'll find it.
That's right. It's an optimization problem in that sense. Yeah, because yeah, like I said, I mean, also another way of thinking about it is by training this model, you have essentially made this into like an expert.
Mhm.
It knows that process. So now you're going to pick its brain like an oracle and say, what about this scenario? What would be the input to that? What about this scenario? And so you're essentially, extracting information from it, being a type of a generative approach. You can also uh in create inputs here, right? And then that's generative in the sense that those could become new inputs to train this model over here with the corresponding output. Yeah. Do you see that? And so that's also a possibility. That's actually a little bit how the passwords thing worked because there may be some situations where you just want to have thousands of that thing for whatever reason. Do you see that? Yeah, go ahead. Mm-hmm.
Not bad.
Yeah, you mean like when you get an input, you can run it through this one and get an output that.
Yeah, the width around, what, move to another way.
Which weights? I'm sorry. I don't understand.
We give what.
Which way? The second or the first way? Step two, okay.
Give what the.
Gives us the wrong inputs. Well, it shouldn't do that, right? Because that's the whole point. It starts random, but as the process moves on, it should be a little bit better. Now, is it possible, like what's going to happen is if this input is not that great because it just can't figure out anything better, then we're gonna have a violation of one of the constraints. So for instance, this one will fail. In that sense, maybe the value here, the real value came to 95. But you have a way of checking this. Do you see that? So, now it just depends on your application because in some applications, okay, it didn't get to 100, but it got pretty close to it at 95. So it just depends, like if of your scenario, right? But there may be it may not meet all of them, but this is something that you have to check. This will be in the second example. I do have this. I've seen this. This has happened to me too, where it doesn't meet all the constraints, but actually, if you look at it, it's pretty close or it's getting there for sure. Okay. Any other questions, guys? So does it make more sense now for everyone? You have a question? Yeah. Yes.
Can try to find something that
Yeah. That's right. We don't do anything to the weights of the model. Yeah, we train it until we have an R square of 0.80 for instance. That's right. That's right. That's exactly right. So the weights of the model are totally respected. This is in fact critical because we're starting with a random vector here, but it's going to use what it learned from this phase to predict this value. Exactly. And so what we're doing is it's predicting, we're comparing, and we're using that information to backpropagate to update the values of the input. And then we do that in a loop, a certain number of epochs until we start to get close, right? To where, and you can check the inputs, the outputs, so that you're approximating what you're wanting. Do you guys see that? All right. So I think that's all the questions. All right. So let's yeah, good questions. So now let's go back and yeah, that was a case that we did. And it's the second example I will do. All right. So let me switch back to the repo. All right, so I think I was saying this, right? This is the code explanation. I will start that in a second, but before that, let's just consider another example. So now I'm going to switch. This is more, not theoretical, but just more high level, right? We've done an example of considering, where this problem has been used quite a bit, which is like chemical, material science, physics even. Okay, now we're going to consider AI models. So this would be like large language models. So NIO for auditing AI models. This actually has been done. There's a couple of papers on this approach, but it's very interesting. Now, before you get lost in this idea, just consider the fact that what were large language models essentially? They were tensor operations, embeddings. Do you guys remember that? They were essentially embedding machines, right? So actually, let's switch to the whiteboard just for a second. So let's remember what a large language model is. An LLM, ChatGPT, etc. Sure, we had text, right? We had text, but we know that we would convert this into tensors, right? And we would essentially have a tensor of number of batches by the length of the sequence, and then each element in the sequence had an embedding of size 256, right? So if we like zero in on just one, right? So let's imagine this is batch 3, and we're looking at the sequence, and we look at the third element there, and that was nothing more than a vector maybe of size 256 or 512. What was in here? Numbers, which are very similar to regression numbers. Do you see how they're just a type of regression number, real valued numbers? Maybe this was a 0.50, and then this one was a 0.75. Do you guys see that? So at this point, sure, it's text, but at this point, it's numbers. It goes through the entire architecture of the neural network of the GPT. So let's just say this is the whole GPT, the heart of it. And then when it comes out, what was it? It was a tensor. Just like the previous one, right? Of batch by sequence length by the embedding. So if we looked at just one of these, it was also an embedding of size 256 or 512. If we zero in on these values, what are they? Regression type values. So this might be a 0.80, 0.70. Do you guys understand? Why am I doing this? Because in NIO, what did we do? We essentially take regression, an input, set of values, right? And an output, which is a set of values. So this is Z. So it's the same idea, right? We can figure out, so the question would be what? What is the set here of values Do you see that? That produces this set of values here. Why do we want to do that? Because that translates that these values here came from text. And these values here go to text. Do you see that? So essentially in between, we could start with a random vector here. Do you see that? The model is already trained, but we freeze the weights. And now we run randomness through this to produce what? A set of values here. When we convert these values to text, guess what? It's toxic language. So what are we doing there, what are we doing there? We're basically start with some random text, goes into the model, which is frozen, produces a thing here of values. When we convert that to text, toxic, right? And so the text initially is probably not going to be very toxic because these are just random, but then via back propagation, we update the values of this vector. And guess what? After many iterations, it starts to look like the embeddings that are produced by a prompt, that when that prompt goes in, it produces a toxic output. Do you guys understand that idea? So essentially the machinery is the same, right? Because we're still just it's more complicated, certainly, right? But this is something that people have done already. So just trying to figure out, what these values are that would produce certainly a vector here of embeddings that converts into, I use toxic, it could be, I don't know, sci-fi lingo, or it's Shakespeare lingo, or a vet GPT, whatever it is, right? But people don't necessarily do research at this level in large language models. They do research at this level because these are numbers and it's, you have certain properties here. Got it? So essentially that's the idea. I'll mention some more things as I have them written down, but this is the essential concept to understand of how they're achieving this. Any questions on what I just said? Okay, great. So no questions. So let's go and take a look at the notes. I did not put the papers in there. I might do that later. But these are a couple of papers. So auditing AI models. So this is work that has been done for privacy leakage and also I think this toxic. So neural input optimization can be used not only to audit security policies like password constraints, but also to audit the AI models themselves. The framing treats the model as a frozen function. So I think all of you understand that. I can freeze a GPT just the same as I can freeze a tiny model. It's super easy. So this framing treats the model as a frozen function that searches for inputs that cause specific outputs or internal activations, subject to constraints. And that's the key, right? So you define what your constraints are going to be. That's your creativity there. Below are two interesting use cases. So the first one, triggering a target output text in a large language model. Use NIO to discover inputs, e.g. embeddings or prompts, that make a frozen LLM produce specific output completions, such as toxic language, jailbreak instructions, or sensitive policy violations. This is a form of automated red teaming where the optimized input is crafted not by manual prompting, but by stochastic gradient descent. It's pretty nice, right? So that's pretty interesting because, maybe you were just thinking of regression, but this is manipulating language. And like I said, images are this even closer to the central idea of this. Okay, so this, it's not just to figure out inputs, as I said, but also to you could generate tons. Let's say you want 1 million toxic examples. You could do it, right? In theory, right? So that's also a possibility. So I'll repeat this part. This is a form of automated red teaming where the optimized input is crafted not by manual prompting, but by stochastic gradient descent, and you just start with a random input tensor in this case, not just a vector. So that's much larger. So GPU power here probably. It allows auditors to systematically search for edge case completions that may not be covered in traditional evaluations. And that's the whole point. Like, people know how to do this or that, but you throw more variables at us, right? And we're limited. This is pure optimization. It doesn't miss any. All right, the second example is kind of interesting, I thought, which makes sense. But think about it. It's kind of like crazy. You grab the large language model, grab it in the middle, like some embed, think, how it's 6 blocks, right? So grab block 3, grab those embeddings. And from there, you figure out what input trained it to obtain that embedding. And essentially what they're trying to do is like, this was less successful, I think, but they were trying to figure out like, where did you learn this from? Like, did you tell me that you found this in the New York, in the Wall Street Journal on page 3, this text led to these embeddings. Do you see that? So that's kind of the idea. So use NIO to recover or approximate the original input that produce a known internal embedding or hidden state. So this one, as I said, not looking at just input and output, but the knowledge of the neural network itself at some layer. I mean, in theory, right? If you build the correct laws for this, you could backpropagate to some input that achieves whatever it is that you're looking for. So that's essentially the idea. It could be maybe that it just by inference, it kind of comes up to, well, this looked like this, and this is something that you find in 4chan. You know what I mean? I don't know if you guys know what 4chan is, but it's like a very toxic Wikipedia type of a thing. So it's very peculiar, right? So you would know what it is. Or manga somehow, not because you go back to the text, but because the text that it produces in the input is very manga. Manga is like Japanese anime, right? Or some example like that. Or maybe you look at it and you're like, this looks like bad Shakespeare or weird Shakespeare. And so you start to like figure out, hey, you know what? Something related to Shakespeare text led to this hidden state here. Do you guys see that? So it's more like that. So this was some research. So as I said, use NIO to recover or approximate the original input that produced a known internal embedding or hidden state. This method tests how much information about the input is retained and potentially leaked through the model's representations. You guys learned from your project that GPT memorizes, right? A lot of you had this conclusion. Hey, it memorized this, it memorized that. So there might be one little piece of the whole embedding that is a memorization. You never know. So this method tests how much information about the input is retained and potentially leaked through the model's representation. So this is obviously for a company like OpenAI, this is a big fear, right? That some secret stuff is going to be revealed of the training that they use, and then they're going to get sued or something. It's useful for auditing risks related to memorization, privacy violations, and information leakage in embedding APIs and transformer models. Imagine that it starts outputting a whole bunch of emails from Boeing because somehow those emails made it to the training set. That's a huge lawsuit right there. You see that? So that's what, not saying maybe no one has found it, but if somebody finds this, they'll partner up with a law firm and they're done. Yeah, go ahead, please.
So it's more like
Here, this one is just about these 3 terms, privacy violations. So we learned, for instance, that GPTs can memorize, but they don't memorize with text that we can read, right? How do they memorize? With embeddings. So what they're trying to do is they don't go to the end of the GPT. They just end it at block 3, that embedding. They find some clever loss function for that, the constraint, and then they try random sets of inputs that hit that third layer embedding, is compared to whatever the loss is, and it just does that in a loop until eventually the input is finished, and then you convert that back to the original text, and it could turn out to be something that looks, like I said, very specific to something, to some language, or to, it has a lot of formatting, let's say, of the way that they write memos at Boeing. So that's the idea. But still, you're trying to figure out what's at the beginning, right? This starts random.
It's kind of like a tracking them.
What's that?
It's like tracking.
It's a way of what knowledge, yeah. Yeah, it's not even about fixing. It's just about like finding something or testing the weaknesses of large language models. Yeah. Let's say, for instance, that some people learn how to do math one way in some countries, and others learn how to do math in other ways, right? So I remember, I don't know if some people would divide, like I divide like this, but some people would divide in, I don't know, let's just say like that. It's some weird way that it was different. To me, this is weird, and to them, this is weird, right? So that's a very big generalization, right, of something that I looked at books that all had examples like this. They looked at books that all had examples like this one. Do you see that? So if you looked at the GPT and its embedding, you could derive that it starts to look all like this. So then it learned for sure from these books and not these books. Do you see that? So that's a more general example. But like I said, they were in the paper, they were exploring memorization, privacy violations, information leakage, and all these things. This is a big problem. I don't know if you guys know, but like Anthropic signed a big agreement with, I think, the New York Times or something like that, for millions of dollars, so that they, settle a lawsuit, I think it was, because they had used their text, and going forward, there's like a paying scheme. So it's big business. Okay. All right. So that, I think, is covered. So these use cases reframe input optimization as a structured, constraint-aware audit tool. Audit tool, hacker, attacking tool, it's either or. Audit tool rather than an adversarial attack, opening up new applications in AI governance, safety, and risk assessments. But you can apply it to many other things. All right, so I think that's kind of just to give you some ideas, some thoughts, right? On now your challenge is to form your groups and figure out what you want to do. Maybe have like a and B, right? A safe one and then a big ambitious one. Or if you're an ambitious, just go with the ambitious one. Like I said, I mean, I just want to see your process. As long as you try hard to, correctly to do it. But yeah, it's up to you guys to pick a data set and try to implement this. Do you have a question? That would generate those, yes. Again, you can only discover them. You don't have to take action, right? So I'm not asking you to make a correction, but as long as you say, I wanted to generate inputs that meet this constraint of the outputs, and guess what? Statistically, I can prove that I did it. Is that useful or not? I'm not asking for that. I just want you to understand the technique. But you can use it for generative, for something fun. It's entirely up to you. Give it a justification, even though you don't actually implement that second stage of how to solve the problem. You know, let's say that you discovered that it's leaking information. Solving that is a totally different project. You know what I mean? Go do a master's degree for that. All right. So yeah, but that's the idea. All right. So I think we're ready now, giving you enough ideas to look at the code. And the code is actually pretty straightforward. I have a code example here that requires no data. All right. So we're going to start with this one, and then we will do one that requires data. Okay. As I said, you can also do this where you don't require a model. You know, I did one where I just had a softmax and that's it, and maybe a relu, I think, but no model, no weights freezing or anything like that. But let's take a look at this one. So this is the code, and it's actually what is 6:11, right? So we take a break at 6:20. So we don't cut this off. Let's just take the break now. 10 minutes. So it's 6:11. Let's come back at 6:21. And that way we can look at the code and just go from there. And I think once you look at the code, it'll start making more sense. This is very simple. Okay. All right. So I'll end this video. Let's take